Rightio, g'day students. Welcome to the lesson today on network flow. So today we want to just solve some small scale network flow problems, including the use of maximum flow, minimum cut theorem in determining the volume of something that can flow through a network of pipes, for example. So some important terminology. A source is the starting node or vertex in a network, and the sink is the end one where it all ends up. The flow capacity is the flow or the volume of flow that an arc can allow. The inflow is the total of all the flows leading to a node. The outflow is the total of all capacities of arcs leading away from a node and all the volume of the inflow, whichever is smaller. Now the network flow capacity is the total flow possible through the entire network, and the excess flow capacity is the capacity of the arc less the flow into the arc. The outflow of node is the minimum value obtained when one compares the inflow to the sum of the capacity of all the arcs leaving the node. So if we have a look at our three diagrams here. So we've got a source and a sink. Now let's have a look. All flow commences at A. It's therefore the source. All flow converges on F, indicating it is the sink. Now B has an inflow of 100. The flow capacity of the arcs leaving B is 30 plus 20 plus 10. So that's got to be 60. So the outflow is a minimum of 160. So whatever's smaller, so 60 is smaller. So that's got to be the inflow. The flow capacity. Now B still has an inflow of 100, but now the capacity of the arcs leaving B is 80 plus 20 plus 30. Now the outflow is still 100. So let's have a look at these two here. Remember, these sum up to B. 30 plus 20, that's 60. But in this case, these sum up to be, 130. But there's only 100 coming in, so the outflow is still only going to be 100. Now, using the diagram below, determine if there is sufficient flow to each node in the network, or vertex if you want to call it that as well. If it's not sufficient, determine if it's possible to solve the issue and describe the solution. So if we have a look here, we can see from A to B is 600, but from B to C there's 100 and B to D there's 300. So the inflow to B is 600, but the outflow is only 400, so there's 200 missing. What else can we see? We can see that from C to E, well, we could do with another 100, couldn't we? There's an inflow of 100, but an outflow of 300. So the flow capacity of C is just, 100, because that's all that's going into it. So there's a few problems with this network here with flows. So upon inspection, there's not a sufficient flow to D. So it cannot be solved as the maximum flow from A, from the source, is 600. And there's not sufficient flow into E as well, is there? So this could be solved by adding an edge with a flow capacity from B to C, or between B and E. So we could go, there's another 200, or another 100, did we say? So we could change that to 200, for example, or we could go that way and add in a bit more. What else can we do? So we could be adding an edge with a flow capacity between B and C, 200, or between B and E, yeah. It would also mean an outflow of 600 from B. Now if we increase that, which is an inflow of 600. Now what could we do from B to D as well? You could change that up, couldn't you? You could change that to 400 and increase the capacity, so the inflow and the outflow are the same. We've got an issue here though, haven't we? Now we should also notice, yeah, that's our source and this is our sink. There's a number of things that we could do to solve this issue here. Now let's convert the following flow diagram to a table. So and then we'll determine the flow capacity. So what we do, we look at A to B, that line. So A to B is 3, and that's what you can see that there. So we just fill that in. Now A to C is 4, yep. C to F is, that's an E, sorry. I can't read my own diagram. Well, let's go here now. B to E. B to E is 2. That's good. I need to also talk about A to D, which is 2. That's good. Okay, now let's look at our C. C to D is 4. Yep. And C to E is 3. Yep. And D to E. Yep. That's 4. So we've now been able to read from a diagram into a table. Now, if we have a look here, the flow from A to B to E has got to be 2, hasn't it? So if we look at that, the maximum of that one could be 2. If we have a look here, A to C to E, well, that's got to be 3 so far, but we can also see we've got an extra one down there. So let's have a look. A to D is 2. But ACD equals 4, and the flow from D to E equals 4. Therefore, the flow from C to D need only be 2, so that's fine. And flow to A to C is 4. Yep. Therefore, if flow to C to D is 2, the flow from C to E is only going to need to be 2. So the maximum flow for this network is 2 plus 2 plus 4, which has got to be a total of 8. Now we can also use a different method to determine the flow capacity of a network. So what we do is just be placing a cut across the arcs of a diagram. We're going to count the value of the arcs and whose directions that point away from the source. So let's have a look at our first cut. You can see here that we've got 3 plus 4 plus 2. 3 and 4 is 7, plus 2 is 9. Let's place another cut. This one we've got 2 plus 4 plus 2. Well, that's got to be 8. Now let's place another cut. So cut 3, we've got a 2 plus 3 is 5, plus 4 is 9. Okay, so the minimum cut is 8, and therefore the maximum flow is 8. That's the maximum amount of stuff that can go through those pipes, for example. Are you able to solve small-scale network flow diagrams, including the use of the maximum flow minimum cut theorem? When you're happy with that, please work on the mastery exercises for today.